Imagine just a single line of malicious code tucked into an everyday input field, maybe a search bar you use all the time. And that one line could unlock millions of private customer records. Or maybe even worse, what if that tiny bit of code could delete an entire company's server? Scary thought, right? Welcome back to the Deep Dive. Today, we're really digging into something pretty persistent, a real digital headache. Injection vulnerabilities. Now, this isn't just theory, it's a critical topic. It always ranks high on the OS Top 10 list. Quick reminder for you, OWASP, that's the Open Web Application Security Project. They're kind of the go-to for web security risks. Their top 10 list is the industry standard, basically. And injection vulnerabilities, they were number 3 in 2021 and actually number 1 back in 2017. So, yeah, still a huge deal. Our mission today is to unpack these things. How do they work? Why are they so dangerous? And the important part, how can we actually stop them? And why should you, listening right now, care? Well, whether you're building software, managing a team, maybe you're just curious about digital security. These flaws, they pop up in about 19% of tested applications. 19%. And they're surprisingly easy to exploit, even without mad skills. The results can be devastating data breaches, huge financial losses, wrecked reputations. Our deep dive today, it's based on this really comprehensive guide, Injection Vulnerabilities. A comprehensive guide is like 20,000 words, a serious piece of work. We're going to pull out the most important bits, the tech details, real-world stuff, how to prevent them, and yeah, a pretty compelling case study too. So let's get right into it. At its simplest level, what is an injection vulnerability?
Right. So at its core, it happens when a system takes input from a user, could be something you type in a form, or even just data your browser sends automatically, and it processes that input using something called an interpreter. Now, think of an interpreter as like a language translator for the computer. SQL talks to databases. A command line interpreter talks to the operating system. If that interpreter isn't careful, if it doesn't check the input properly, it can get tricked. It might mistake malicious user input for a legitimate command, and then poof, it executes something harmful instead of just handling the data.
Okay, so it's like whispering a secret malicious command into that translator, and the translator just goes off and does this bad thing thinking it's a normal instruction.
Exactly like that. Yeah.
That makes a lot of sense. And you mentioned interpreters. What kinds are we talking about here? Where can this trick actually work?
Precisely. The guide, it highlights several key ones. SQL for databases is a big one. OS commands for the operating system itself, even things like LDAP for directory services. And the potential consequences, like you hinted at, they're severe. We're talking major data breaches, losing all your data, systems getting completely compromised, or attackers getting access they should never have.
Wow. Sounds like stuff straight out of a spy movie, honestly.
Yeah.
So what are the most common types, these injection attacks you might actually run into?
It's actually fascinating how many different flavors there are, but they all boil down to that same idea: tricking an interpreter. First up, probably the most famous, is SQL injection. This targets databases. Very common. Imagine an attacker at a login screen. Instead of their username, they type something like OR11.
Okay.
If the system's vulnerable, it might read that as find a user where the username is empty or where 1 equals 1. Well, 1 always equals 1, right?
That is true.
So boom, they bypass authentication, they're in.
Just like that. Wow.
Then you've got command injection. This one lets attackers run operating system commands directly on the server. So if an application takes user input, maybe a file name, and uses it in a system command, an attacker could sneak in something like iter_mrf.
Uh-oh. I know what AirVirF does.
Yeah, exactly. It tells the server, okay, finish what you were doing and then delete everything, starting from the top. Could wipe critical files or worse.
Nasty. What else?
Well, there's NoSQL injection. This is a bit newer. Targets NoSQL databases like MongoDB. Here, an attacker might inject something like null into, say, a password field. It's not exactly code, it's a query structure. It basically tells the database, match any user where the password is not null. So if anyone has any password set, it might let the attacker log in as them.
Sneaky. Different logic. Same outcome.
Exactly. And there's also LDAP injection. This is for systems using LDAP for authentication, managing user directories. Attackers can mess with the LDAP queries. For example, injecting something like itery beated. It looks like gibberish, but
It does something bad.
it basically tells the directory, forget the specific user, just give me all the user records you have. So they could potentially dump the entire user list.
Okay, so the guide also mentions cross-site scripting, XSS. That feels a bit different. How does that fit in? Is it still an injection?
That's a great question. Yeah, XSS is often seen as client-side, meaning it affects your browser, not the server directly. But it is definitely a type of injection. What happens is malicious scripts, like say, script alert, you are hacked, script, get injected into a legitimate web page. Then when you visit that page, the script runs in your browser. It might steal your session cookies, redirect you to face the site for you. It's injecting code into the web page that your browser then executes.
Got it. So it's injecting into the page, targeting the user's browser.
Yeah.
Makes sense. It's fascinating how varied these are. But, before we jump to prevention, I'm wondering, why are these still so common? With all these known attacks, what are the basic mistakes that keep happening?
Yeah, it's a really important question. How do they keep occurring? The absolute number one culprit is something called direct input concatenation.
Concatenation.
Yeah.
Like just sticking things together.
Exactly. Just mashing or stitching user input directly into a command or a query string without treating it purely as data. The guide gives this classic PHP example. Imagine code like select from users, where username as username and password equal password.
Okay. Seems standard enough.
But if the attacker enters admin as the username, see that single quote and the double dash?
Uh-huh.
The single quote closes the username field early, and the in SQL means comment out the rest of this line. So the database only sees select from users where username equal admin. The whole password check just gets ignored.
Oh, wow. So they just log in as admin, no password needed?
Bingo. Simple as that, if the code's vulnerable. Other big factors, just a general lack of really strict input validation. Also, wrongly trusting data that comes from the client side you can never trust what the browser sends, and not properly escaping special characters like that single quote. Common targets are databases, sure, but also operating systems, LDAP servers, and these days, modern APIs are a huge target.
Okay, this is where it gets really concrete, because these aren't just, code snippets in a guide. They happened in the real world. In 2018, Panera Bread had that huge data breach. That was SQL injection, wasn't it? What happened there?
Yeah, that Panera case is a really stark reminder. In April 2018, they disclosed a breach. It affected something like 37 million customers. But what's really worrying, and the guide highlights this, is that the vulnerability itself was found and reported way back in August 2017 by a security researcher.
August 2017. So they knew about it.
They knew about it, but Panera apparently didn't fix it for 8 months. 8 months.
8 months. That's a long time for a door to be left wide open. How did the actual exploit work?
It was an equal injection flaw on one of their API endpoints, specifically app customer. It was used for managing customer accounts online. The basic problem was the system took that customer value from the URL and just plugged it straight into a SQL query without cleaning it first.
So direct concatenation again?
Exactly. Attackers could manipulate that ID. Instead of just 123, they could put in something like 123 union selected name, email, phone from customers.
Ah, the union trick, grabbing extra data.
Precisely. It let them tack on their own query to dump out customer data names, emails, phone numbers, everything associated with other IDs. The critical failure was no parameterized queries, no proper input validation on that ID.
So what was the fallout for Panera, and obviously for the 37 million customers?
Well, the breach exposed really sensitive personal info, names, email addresses, phone numbers, birth dates, even partial credit card numbers in some cases. Yeah. Panera faced, huge reputational damage, massive legal consequences, lawsuits, significant financial costs for fixing everything and potential fines. Plus, it brought a ton of regulatory scrutiny, really highlighted how crucial compliance with data protection laws like CCPA in California and GDPR in Europe is. Companies have to protect that data.
Okay, so hearing about that kind of devastating impact, it really brings it home. What does this mean for actually preventing these attacks? How can organizations protect themselves, protect their customers, avoid being the next Panera?
The guide lays out some really clear, solid prevention techniques, and the single most important one, it's adopting secure coding practices. Specifically, using parameterized queries, or sometimes called prepared statements, especially for SQL databases.
Parameterized queries, we hear that term a lot. How does that actually stop the injection?
It's fundamental because it forces a separation between the code, the SQL command, and the data, the user input. You basically tell the database, okay, here's the query structure, it has some placeholders, and then you say, and here's the data to fill into those placeholders. The database knows the second part is just data. It will never interpret it as part of the command, no matter what characters are in it. That single quote, the double dash, they just get treated as literal text in the username field, not as special SQL commands.
So it kind of defangs the malicious input, treats it like dumb text.
Exactly. It neutralizes the attack vector right there. The guide shows a Python example using slight 3, where you use question marks as placeholders, like cursor.execute, where username and password equals that, username, password.
Yeah.
That tuple, username, password is sent separately.
That seems almost too simple. Like, it's been the recommended practice for decades, right?
Yeah.
So why do companies still struggle with this? Does the guide shed light on that? Why isn't it just universally done?
That's a really crucial point the guide gets into. It's not always just about knowing how to do it. Sometimes, especially in large, older code bases, you have legacy code that wasn't meant that way. Refactoring takes time and money, and, the pressure of agile development cycles can sometimes lead to shortcuts. Maybe a quick fix gets put in that uses string concatenation because it seems faster. Or sometimes complex reporting tools or data analytics platforms might have their own ways of querying that bypass the standard application security controls. So new vulnerable entry points can appear.
Oh, okay. So it's not just the initial development. It's maintenance, it's third-party tools, it's the whole ecosystem.
Right. The guide really stresses that the challenge isn't just the technical how-to, it's about embedding secure practices deeply into the development culture, making it the default. Having automated checks in the build process that flag raw SQL queries, making it really hard to even ship vulnerable code. It's a cultural shift as much as a technical one.
Makes sense.
Yeah.
So beyond parameterized queries, what else?
Well, rigorous input validation and sanitization is absolutely key. You need to strictly check inputs against what you expect. Like if you expect a zip code, only allow numbers and maybe a dash, right? Reject everything else. And sanitization means cleaning the input. Using trusted libraries, the guide mentions OWASP Java encoder or Python's Bleach to remove or neutralize potentially harmful characters before they even get near an interpreter.
Okay, validate and sanitize, defense in depth.
Exactly. And then there are architectural best practices. Implementing the principle of least privilege is huge. Your web application's database account shouldn't have permission to delete tables, probably. Give it only the absolute minimum permissions it needs to function. Read-only access where possible.
Right. Don't give it the keys to the kingdom if it just needs to read the guest list.
Precisely. Also, deploying web application firewalls, or WFs. Things like mod security. These act like a shield right at the edge, filtering out obviously malicious requests before they even hit your application code. And for servers themselves, disabling dangerous functions if you don't need them, like PHP's exec or system, which can run OS commands, is just good hygiene.
Oh.
Reduces the attack surface.
Okay, so that's how you build the defenses. But how do you find out if you already have these problems? How do you test for injection vulnerabilities?
Yeah, testing is critical. There are some great tools and methods. For automated scanning, tools like SQL Map are laser focused on finding SQL injection flaws. Then you have broader web vulnerability scanners like Burp Suite or OWASP AP. These are invaluable for finding all sorts of issues, including various types of injection.
So automated tools are a good start.
Definitely. But manual testing is also crucial. This involves a skilled tester methodically poking at input fields, trying different special characters, malformed data, looking for error messages or weird behavior that indicates a flaw. Sometimes the automated tools miss subtle things.
Right, the human element.
Absolutely. And critically, these testing techniques, both automated and manual, need to be baked into your CI/CD pipeline, your continuous integration and deployment process.
So testing happens automatically as code gets built.
Ideally, yes. Using static analysis tools, SAIST, like SonarQube, that scan your source code before it's even run, looking for dangerous patterns. And dynamic analysis tools, DAST, like OWASP ZAPI, integrated into the pipeline that tests the running application by simulating attacks. Catching these vulnerabilities early during development is way cheaper and safer than finding them in production, like Panera did.
Definitely sounds like the way to go. Integrate security right into the workflow. Now, it feels like the tech landscape is always changing. Microservices, serverless, cloud stuff. How do injection vulnerabilities fit into these modern, more complex environments? Are they still a big threat there?
Oh, absolutely. Injection isn't going away just because the architecture changes. In fact, modern setups can sometimes introduce new complexities. Think about microservices. You have lots of small services talking to each other via APIs. Every single one of those API interaction points needs robust input validation, especially if they're handling things like JSON or maybe GraphQL payloads. A vulnerability in one small service could potentially compromise others.
So the attack surface might actually be larger.
It can be, yeah. And serverless functions. If they take user input and pass it to a runtime environment or use it to query a cloud database without proper checks, they can be just as vulnerable. Same principles apply. Lax configurations in cloud services can also open doors. The guide also flags some emerging threats, things like GraphQL injection, which is specific to how GraphQL APIs handle queries. Attackers can manipulate those queries to pull data they shouldn't see, and even the rise of AI-powered attacks. Imagine AI tools specifically designed to find and exploit injection vulnerabilities automatically at massive scale. That's kind of scary.
AI attacking systems. Great.
Yeah. And we can't forget IoT devices, Internet of Things, smart cameras, thermostats.
Hmm.
These often have very basic security, run lightweight operating systems, and take direct input. They can be prime targets for command injection or other flaws.
So the core problem persists, it just adapts to the new playgrounds.
Pretty much. The underlying principles of validating and sanitizing untrusted input remain absolutely critical no matter the tech stack.
Okay, we've really covered a lot of ground here. We've dug into what injection vulnerabilities are, seen how common they are, the kind of devastating impact they can have, thinking about Panera Bread again, and crucially, the steps needed for prevention and testing. The fact that these vulnerabilities, they persist, even though they dropped from #1 to #3 on the OWASP list,
Yeah.
it really underlines a critical point. Security isn't just a checkbox. It's not a one-time fix. It's this ongoing, evolving process, right?
Absolutely. Constant vigilance.
And thinking back to that Panera Bread breach, that agonizing 8-month delay after the vulnerability was reported, it really makes you think, doesn't it? Beyond just the technical fixes, the code changes. What's the broader responsibility? What's the, maybe, moral or ethical imperative for companies when a serious flaw is responsibly disclosed, especially when millions of people's private data is on the line? How does the delay like that change how we as customers trust companies? And maybe more personally, what lessons should you take away from that when you're deciding where to share your own personal data online? Something to definitely mull over.